Okay, so let us discuss the next idea, what we call the Fourier transform. We read it Fourier, but mostly when you listen to some foreign mathematicians, the people from Europe, they call it Fourier transform. Like the last R is silent. So whatever it is, we are not concerned about the exact pronunciation, we are concerned about the mathematics. So Fourier transform is another transform which is going to be very much important. And the importance comes from the transform which basically runs on the whole real line, or the what we call the whole x-axis, or the domain from negative infinity to positive infinity. Because in Laplace transform, what do we have? We have domain from 0 to infinity, but here we have domain from negative infinity to positive infinity. And it is mainly used to solve partial differential equations, because if the length of some rod which is heated is infinite, it means it goes from negative infinity to positive infinity, and we are going to solve the particular heat equation related to that, then we apply Fourier transform. Because if the domain of the equation is from minus infinity to infinity, we cannot apply Laplace transform for that. It's not possible. So there are some things which should be kept in mind. You have heat equation, the domain is from negative infinity to positive infinity, you can apply Fourier transform. If the domain is from 0 to positive infinity, you can apply Laplace transform, you can apply Fourier sine transform and Fourier cosine transform, because they are applied from 0 to positive infinity. And when can we apply the what we call the method of separation of variables? We know very well. We can apply that on heat equation, wave equation, when the domain is finite. When the domain is from, let's say, 0 to fixed L, then we can apply separation of variables, otherwise we can't apply. So there are some methods and there are some restrictions for every method. There are some good things about this one and there are some bad things. So we'll be discussing both. And one thing that is crucial here, we have Laplace transform of the functions which are unique. Like you have Laplace transform of sin t, that will always be like 1 over s square plus 1. But Laplace Fourier transform are not unique. That's why mostly in any exam, it is not mostly asked that, okay, what is the Fourier transform of this thing? The problem is it is not unique. And why it is not unique, we will be discussing. I have my own Fourier transform of one function. You have your own. Then what we are supposed to put in our exam? That's a problem. So they mostly never ask these questions. But they can ask the properties, they can ask the formulas, they can ask the restrictions, okay, where can we apply, where we can't. So these things are there. Otherwise they don't ask a specific question. So I have a few things to discuss. Maybe we will not be able to discuss everything, but let us discuss the main points. So to define the Laplace Fourier transform, there are some conditions for a function to be followed. The conditions are called Dirichlet conditions. So a function f of x is said to satisfy. So f of x is said to satisfy Dirichlet conditions in the interval, let's say, when x runs from minus a to plus a, if number one, f of x has only finite number of finite discontinuities. Number two, f of x has only a finite number of maxima and minima in this interval. So these are what we call the Dirichlet conditions. So if a function satisfies these conditions, we call that the function satisfies Dirichlet conditions. Can you tell me what do these conditions mean? The first one is f of x has only finite number of finite discontinuities. Or you can give me counter example as well. Like you have a function, it's discontinuous here, it's discontinuous, then it goes like this. So it's discontinuous here, it's discontinuous here. But these discontinuities in some interval should be finite. Like one discontinuity, 2, 3, 4 and so on. But these should be finite. And the next thing is finite number of finite discontinuities. What does it mean? Sometimes what happens that you have a function at some fixed value of x, there is some sort of asymptote. We know very well the function goes like this, and here the function comes down. So this is what we call the infinite discontinuity. It is not finite discontinuity because exactly at this value the function explodes. So this is the infinite discontinuity. So the function has finite number of finite discontinuities. This is infinite discontinuity. And what do we mean by finite number? If you take this function, the function takes value 1 and 0. 1 when x belongs to rational and 0 when x belongs to irrational. Now you have some interval a to b. Let's say this is rational, so the value of function is 1. Value of function is 1. In between sometimes it is 0, 1, 0, 1, 0. Because at every instant you have some rational value and some irrational value. So these are what we call the infinite discontinuities.
Tangent you graph would have to be infinite.
Yes, infinite discontinuity. But in the whole domain from minus infinity. If you restrict your domain, let's say from 0 to 2 pi, then the number of discontinuities is finite, but those discontinuities are infinite because it goes to positive and negative infinity. Asymptotes.
ऐसा वो ceiling function जब बोल दो जो
finite in some interval.
वो finite होगा.
In some interval. Second condition is f of x has only a finite number of maxima and minima. Can you give me any example which has infinite number of maxima and minima within some interval? Because when we discuss something, we have so many examples, but we should think for some counter examples. And the counter example for this is sine of 1 over x. Because you know very well, I think this comes like this and comes like this, but within then this short interval it has some jiggling behavior within this. So between this interval, let's say a and b, it has some maxima and minima which are infinite in number. You can see the graph with the help of Desmos and you will come to know that okay, what happens exactly. So when function satisfies these two conditions, we say that the function satisfies Dirichlet conditions. Okay, with the help of this, we can define we can state the Fourier integral theorem. So the Fourier integral theorem. So we say that if f of x satisfies Dirichlet conditions in this. Now you have these conditions on this whole real line, not from minus a to a, but from minus infinity to positive infinity, and is absolutely integrable on minus infinity to infinity. Then what happens? Then what do you mean by absolute integrable on this? You have a function that is absolute integrable on this. So you take your function, you take its absolute value, you integrate from minus infinity to infinity, this thing should be bounded. We call this function to be absolute integrable on this interval. Sometimes this word is square integrable. Then you square your function and integrate, it should be bounded.
Absolute integral means bounded.
Absolute integrable means you take the absolute value and you integrate, the result should converge or it should be bounded. And we can define then in function analysis that the functions which are absolutely integrable are in the class of L1 and the functions which are squarely integrable are in the class L2. And I think the function which is L1 is also L2. We can define these things as well. So then what happens? Then 1 over 2 pi integral from minus infinity to infinity of e raised to I k x, and I'll write this thing on that side, please. So then what happens? That minus infinity to infinity 1 over 2 pi e power I k x, and then there is another integral minus infinity to infinity with, let's say, f of xi and e power minus k xi and dxi dk is equal to something. And what is that something? That's a function. It means you can represent your function in this integral notation if the function satisfies these conditions. And why these integral representations are so much important? This integral representation comes from the Fourier series. Fourier series, one thing, it is discrete. We know very well, because we know very well it's a series and the sum runs from 1, 2 and so on, so it's discrete. And it's the real Fourier series. One thing is that when we make the discrete thing continuous and make that real Fourier series into complex Fourier series, then we reach at this. And this is related to Fourier transform. And we'll see that how it is related. But this is the theorem what we call the Fourier integral theorem. According to the theorem, this thing is equal to this idea. You have to tell me what does it mean. What does it mean? I said this is equal to f of x. I said this whole is equal to f of x, but I'm not writing f of x, I'm writing something else. What does it mean? F of x plus 0 means the limit of the function at x from the right hand side. The limit of the function at x from the right hand side, plus the limit of the function at x from left hand side, and this is their average. At is divided by 2, this is their average. So what does it mean basically? So this is, let's say, limit of the function from left, this is the limit of the function from right. Now, you know very well when you have these functions, we call these functions to be having finite discontinuities. We can find out their Fourier series, even we can find out their Laplace transform as well as Fourier transform. Now, this condition tells that take this value, take their average means this. It means this whole integral will not converge to this, but the average of this means center. If you study Fourier series, this particular gap is called Gibbs phenomenon. When you study Fourier series, this is called Gibbs phenomenon. The name Gibbs phenomenon. We will come to Fourier series, but we are discussing Fourier transform because it is related to Laplace transform. I am telling these all the things because these might appear in some exams. What do you do when you are given some crazy function like this? you approximate this function with some sinusoidal functions. Then what happens that your sinusoidal function approximates this like this like this. But there is actually the problem in this interval. So there is a jump, and this jump is called Gibbs phenomenon. So leave it as it is. Now what happens that at this x, exactly if the function is, let's say this is x, the function is continuous, it is not discontinuous. Then what is the left limit and what is the right limit? Same. Then this thing will be equal to f of x. You know very well, this is f of x, 2f of x divided by 2 f of x. So this integral representation is exactly f of x if there is no such type of Gibbs phenomenon, and if there is Gibbs phenomenon, then this is average. This is what we call the Fourier integral theorem. Now what happens basically, you can see this is my function. Where is my function in this one? My function is this. You multiply with this, you integrate, then basically this integral inside this bracket transforms your function into, let's say, some other function, and let me name that function capital F of k, because the variable is, the parameter is k. Then what do? You put this f of k here, then you integrate again. Now this is your kernel. First this was your kernel. You integrate again, you take your function back. This is the idea. In this bracket, you put your function, you integrate, you get some another function. It means your function has been transformed, and this is called what we say Fourier transform. Then you put your function back in this, and you transform, you get your function back. So you put your function here, this is called Fourier transform. And this outer thing is called inverse Fourier transform. So in this integral representation you have both formulas. What is the problem? Why I said this is not unique? The problem is this. In some books you will get this 1 over 2 pi with this integral. Some people are taking this and writing this with the inside integral. It's a constant, you can shift it anywhere. But in some books, this is divided into two parts. Like they are saying, okay, write 1 over the square root of 2 pi here and write 1 over the square root of 2 pi here, so that everything is going to be balanced. That's why I said that Fourier transform is not unique, because of this factor, 1 over 2 pi. So it depends upon the notions. Some electrical engineers may be using some one notion, and mathematicians using another notion, physicists using the third notion, but it differs. But there is no any problem with the result. So you have a function f of x, you are going to find its Fourier transform. What is the formula? What is the outside factor? 1 over the square root of 2 pi minus infinity to infinity f of x. I am writing the same thing, minus I k x dx. This is the Fourier transform of a function. Yes, and this Fourier transform would be some function of k. I have written the same thing, just I have changed this xi into x. It doesn't make any difference. But I have given this factor 1 over the square root of 2 pi here. So what is the inverse Fourier transform of, let's say, f of k and inverse Fourier transform? So I will write this outside integral 1 over square root of 2 pi minus infinity to infinity f of k. This is f of k e raised to I k x and dk, which is going to be f of x. So these are the formulas for Fourier transform and inverse Fourier transform. These come from this integral representation. The product of these coefficients must be 1 over 2 pi. The product of these. So some people write here 1 over 2 pi, here they don't write anything. Sometimes they write 1 over 2 pi here they don't write anything. Sometimes they write in this way. It depends. Okay, when can we find out the Fourier transform and when we can't? We are not interested in the Fourier transform of these special functions. I told you the reason is it's not unique. So why should we do some hard work on finding these integrals? We have to do integration, and the integration would be very problematic in this situation. And Fourier transform is the special form of Laplace transform. Because in Laplace transform, S can be complex. Complex means alpha plus iota beta. But here what you have? You have only imaginary part. You have only imaginary part. But in Laplace, S is complex, means real and imaginary both. So this is the special type of that. Some people do like that and say like that, otherwise they are not related.
Sir, excuse me.
Sir,
बॉक्स में लिखे हुए वो नेक्स्ट स्टेप क्यों आ है जनरलाइज क्यों दो ना
this is the theorem
ठीक है
statement
ठीक ही चले
with this.
ठीक वो चले वो क्यों पढ़ेगा
Then these are just the formulas to calculate Fourier inverse Fourier.
ठीक वो उन्हें somehow
But these formulas come from this. These are the formulas.
Sir, just means Fourier transform का हमें complex form है.
Yes.
ऐसे तो Laplace transform में complex भी आएगा
Yes. This is like a special case. But mostly we learn Laplace transform by taking S to be real. Otherwise we can take S to be complex.
So जैसा means any point के लिए हम mind में रखना how we can clear our concept ये का starting में गाल कही तो minus infinity on real axis. So ये complex में तो ये y axis का
That's the problem. I told that some people say that okay it happens like that. Otherwise it is not. It is not actually. Because in Fourier transform you take the function with time domain and you convert it into S. We call T to be time domain and we call S to be frequency domain. Here we have the same idea, but here the idea is a bit different. You take the function with X domain and you know very well X runs from minus infinity to plus infinity. Time runs from 0 to infinity. That's the problem. Here you have function in X domain, in Laplace you have function with time domain. That's the problem. So these things differ. There are similarities, but it is not related to the level of mathematics. When we study physics, we can say that okay, this happens, that happens. Okay, one or two last things that I need to discuss. Can we find out the Fourier transform of every function? Like we can find out the Laplace transform of most of the functions excluding a few. Can we find out the Fourier transform of every function? The answer is no. There are very much like good problems related to this one. You cannot find out the Fourier transform of constant functions, of sinusoidal functions like sin x, cos x. You cannot find out the Laplace transform of exponential Fourier transform of all the functions. You cannot find out. And then the condition is f of x must be absolutely integrable, then we can find out its Fourier transform, otherwise not. F of x must be a, let's say, dash function. And what is that function whose Fourier transform we can find out? From the very basic theory, most of the books call that should be somehow, let's say, a good function. Now good is not in the sense of English that okay, it's a good function. But good function is some sort of function whose Fourier transform we can find out. But this is very basic theory. If we go in advanced level, this good function is what we call a generalized function. And then we define other ideas that what are distributions and so on. These distributions are not from the probability theory. These are the distributions which are used in Fourier analysis and partial differential equations. But there are some functions whose Fourier transform you can find out. Those functions can be called some good functions. We are coming to that. What is that? One property of this good function is that it should be like converging to 0 first as compared to some x power minus n. It means it should be a function that converges to 0 first as compared to, let's say, x power minus n, or what we call 1 over x power n. This converges to 0, we know very well, when x goes to infinity.
Yes, sir.
When x goes to infinity, 1 over x power n converges to 0. But your function or a good function should converge faster than this one. Yes. For example, what is the example? You can find out the Fourier transform of this function. Does it go to 0 as x tends to infinity? Obviously. Yes. Yes, because its behavior is, when you go to positive infinity, this should converge to 0, and when you go to negative infinity, this also converges to 0. So this should be the behavior of the function. If this is the behavior of the function, we can find out its Fourier transform. Otherwise, we can't. So this is what we call a good function x. Okay, so let us reserve a few things for the next class.